try and understand how to turn these like chemical reaction schemes that are going to be the sort of core of how we approach looking at biological systems, and how to turn those chemical reaction schemes into the mathematical language, right? And since this is the title of this class is the physics of living systems, right? So the first thing that we will want to do is that actually establish the physical basis for that conversion from those reaction schemes to the mathematical language we're going to use, right? And so today's, this class is funny, right? It's sort of equal parts biology and physics. And so there'll be some days that the biologists in the audience are going to like, oh my God, what are we doing? There'll be some days the physics students in the audience will do the same thing. So today is going to be a more sort of physics-heavy presentation of stuff that I think you already think you know, but it's always worth going through this once so you know what's under the hood of these kinds of abstract descriptions. That's one thing. And the other thing to know is in week 6, when we start looking at things like random events in biological systems, this stuff that we're going to go over today is core to being able to actually work on those kinds of problems. So the payoff, so we're going to do this today. You're going to say, oh my God, we did this, and 5 weeks later, finally you're going to see the payoff for why we're doing this now. All right, so let's start with an even simpler reaction scheme than what we had last time. So let's suppose we just have the following. We said A plus B, 2 molecules. They react with some rate K to form C. Almost as simple as you can get. Now, probably when you studied this kind of reaction in like freshman chemistry or something, what they would do is they'll draw some kind of diagram where on the y-axis you have something about energy, and on the x-axis there's this like totally obscure thing called reaction coordinate, which I still don't really understand what that means today. Right? And then they draw a diagram kind of like this, right? Where you have the 2 species, they have to go over some barrier, and then you make the product C, right? And then there's this hill you gotta overcome called the activation barrier, right? That's it. This description might be familiar to you if you've taken sort of freshman chemistry. Okay, so this is nice. It gets you pretty far, right? Just with pictures and stuff. It gives you a lot of important concepts. But the question that people who really want to get into the physical basis of these kinds of reactions is, where does this actually come from? Where does this picture arise from a more molecular kind of microscopic description of these kind of systems? And the place this stuff arises from is, it goes under a lot of different names, but the name you'll see most often is this thing called collision theory. And what is collision theory? If I write down here, can you guys see? That's all right? Okay. So to really sort of make this picture more sort of physically interpretable, let's imagine that you have these A and B molecules sitting in some box. Right? Okay. And in this box, you have, we'll model these A and B as little balls. So, in describing a bunch of particles that are sitting in a box, what are the 2 most important sort of properties that you need to know in order to describe this microscopically? So go back to freshman physics now. So what are the 2 things that you need to know about a particle?
Temperature.
What's that?
Temperature?
Okay, it's related to temperature.
Elasticity.
Okay, that's even more detailed than what we need.
Position and momentum.
Exactly. So we just need to know things like positions and velocities and masses, right? So position and momentum are the sort of we have these particles bouncing around. Right? And what we really want to know is, we want to know how to describe, how these things collide, and then actually break this activation barrier and make the product. Right? That's really the heart of chemical kinetics. So those two processes combined, the frequency with which A and B collide, and the fraction of times those collisions actually produce a productive collision in terms of making a product, that goes by the name of a rate, right? That's what that K really is about. So the rate of the reaction is the number of times A and B collide times the fraction of those collisions that achieve a threshold or activation energy. Okay, so very conceptually, this is the quantity that we want to use sort of microscopic physics in order to compute. And then once we've mastered that, we can sort of abstract away these details and just focus on sort of chemical reaction schemes and just use this. Okay. So, but if you take nothing away from other than this, that will suffice for now, right? So that's where these rates come from. Okay. So to start with, let's individually compute using microscopic physics and a little bit of thermodynamics. How do you actually get down a formula for each of these two products that we need to know about? So first, how do you get the number of times? And remember, this is all going to these particles sit in some volume also, so we'll have to normalize all these things by the volumes. We'll get into all that later. But for now, let's just focus on the number of times A and B collide. Okay. So this itself can be broken down into two pieces, right? So the number of times is going to be the frequency with which they collide times the number of colliders right? The number of, collisions actually. Okay? And everyone sort of with me still? So at this very microscopic level, right, we have to now add some detail into these particle descriptions to tell us what does it even mean for it to collide, right? Things don't actually touch, right? So there's there's electrostatic forces and all kinds of microscopic physics you have to worry about to really get this description precise. So what we're going to say is that two molecules are said to collide if they are sufficiently close. What does that mean? So let's say that that for a particle, it has some radius A, so it's a ball of radius A, and the B particle is some ball of radius B. Then we're going to take as just an operational definition that two things collide when when the two particles get within the sum of the radiuses of each other. And that quantity we're going to call sigma AB, which is just the sum of the radii. So if one ball gets within sigma AB of another ball, we assume a collision has occurred. Okay? So what does that mean? So now, if you follow, remember what we're trying to compute. We're trying to compute this collision frequency, right? We're trying to compute how often two things will collide. So what we can do then is we can say, okay, let's imagine we're running this this as a movie for a short time step, right? If you run this as a movie for a short time step, what will happen is that these balls, as they're going around, jostling around in this box, over short time steps, they're going to sweep out volumes, right? They're going to sweep out volumes in which the collisions can occur. So you take this ball, so let's take the radius A as an example. So at a short amount of time, this ball will sweep out this volume of space, right? And if another ball comes within sigma AB of this space that's swept out, then we'll say a collision has occurred. So the fundamental object that we want to compute is, this collision volume. And this collision volume is going to be just the volume that's swept out by this ball. So what's your guess as to what the shape is of this? It's a cylinder, right? It's just a cylinder. So, and the cylinder is the product, right, of the circle that's at the end of the cylinder. So if I'm going to write down the volume, then I can write down the area of the circle at the end of that cylinder times the length of the cylinder, right? And remember, we want collision frequency. Okay? So that's going to have units of per time in it also, right? So the length that's swept out per unit time, what's length divided by time? Velocity, right? So really, this is some average velocity that these particles are undergoing, right? So the collision volume is, in the end, given by something like this, right? So it's the amount of volume swept out by one of these particles. Okay? Everyone with me so far? Okay, that's all nice and fine. But now the question is, okay, how in the world do we get this? Okay, I've sort of like substituted one mysterious thing for another now. Now, okay, this all makes sense probably. This is all geometry. But where does this come from? Where does the average velocity come from for a bunch of particles in a box? So now we get back to the suggestion that was coming before, temperature, right? And what does temperature have to do with average particle velocities? Anyone remember these kind of relationships?
Temperature is the average kinetic energy of the particles.
Exactly, right? So temperature is the average kinetic energy of the particles. So temperature has something to do with the kinetic motion of these particles, okay? So if we're gonna compute the average velocity, we have to know something about the distribution of velocities of these particles at a given temperature. Right? And from that distribution, we can actually compute averages. Right? Okay, so say, so how do we get okay, so if I give you a probability distribution, do you know how do you, does anyone remember how to take, so if I give you a probability distribution, how do you get the average out of that? Do you remember?
Multiply the quantity you want, average times probabilities, and sum.
Exactly, right? So in order to get this average velocity, what we need to do is take the velocity itself, the thing we want to get the average of, multiply it by that distribution of velocities that we know. And then we want to sum across all the possible velocities. So, but okay, now velocities, right, we can agree are sort of, they're not discrete objects that we can sum over, right? So velocities are continuous. So actually what we'll do is we'll replace this sum with an integral over all the velocities, v dv. So it's an integral over all the velocities possible. Okay. And now this problem boils down to knowing how to get this p of p, right? We need to actually have this distribution in order to do this integral. So the derivation of this probability distribution is something that is sort of beyond the scope of what we're going to talk about. Okay? This is something you can learn about if you take sort of intermediate statistical mechanics or thermo. But this distribution it goes by the name of the Maxwell-Boltzmann distribution. And this distribution pops out exactly of the kinds of concepts that you guys have been talking about and telling me about, right? So it's about how temperatures relate to the energy of the system, which is a function of basically the momentum of the system, right? Of the particle velocities and masses. And it turns out that this distribution has the following functional form. So it's the square root of so you'll see it's the square root of the mass divided by this energy scale. Four pi v squared times e to the minus 1/2 mv squared over kbt. Okay, so this is just for any time you do thermo or anything, this is a kind of useful distribution to know about. So there it is. And you can see like that a lot of the concepts they pop out right away, right? So you know you'd expect, for example, that in a distribution of particle velocities, that as you get to higher and higher velocities, there'll be fewer and fewer particles there, right? And this is just a formula for the kinetic energy of a particle, right? So basically, there'll be fewer and fewer particles at these very high kinetic energies, right? So now what you can do is you can just literally plug this into this integral, integrate that out, and you can do it too if you want at home. It's not that edifying for us right now, but what this boils down to is so if you go ahead and actually do that integral out, you get that the average particle velocity is equal to the square root of 8 kBt over pi m. The integral isn't actually that bad, it just involves a little bit of integration of the parts, if you remember that from sort of calculus. Okay. So we've made some progress. So now we have a formula for the average particle velocity at some temperature, right? So, and we have a formula for the collision frequency that we can take our velocity formula and plug it into, right? So now, we can go ahead and do that. And so what you get is that the collision volume is equal to pi AB squared, so that the area of one of those balls, times 8 kBt over pi m. Okay? Okay, so that takes care of this part of it. So we have the collision frequency part sort of nailed down for a given particle, right? But now we want to know, like, okay, so for one particle that's fine, but we have, like, let's say n, you know, NA of the A particles, NB of the B particles. So what's the overall sort of bulk rate of collisions? So this is for part one, and now for part two, for the number of collisions. Well, that's just basically going to be NA times NB, right? It's just the number of ways two of each particle can collide with each other. Okay. But we want to normalize this by the system size, right? Because the number of collisions is going to go down if you have a bigger system, right? Because there are going to be fewer of these interactions that will happen, right? So each of these gets normalized down by the volume of the system. Okay. And what's another word for this ratio of the number of something in the volume of the system? Density, or in chemistry they call them concentrations, right? So this is just literally the concentration of A times the concentration of B. Okay. So that's good. So now for part one of this overall, remember, this overall rate we're trying to compute, we have an answer, right? For part one, the number of times A and B collide, we have that it's the collision volume, so pi AB squared times 8 kBt over pi m times the concentration of A times the concentration of B. Okay? So this is hopefully already looking like pretty promising to us, right? Close to what we ended up with last time. We were just directly translating reaction schemes into rate laws. Okay. Okay, so that term now is picked up. So we've got that part. So now how about the second part? The fraction of collisions. this is where the same trick we actually use with the velocity will actually show up in this in the fraction of collisions above a threshold energy. So in this box of particles that are sort of randomly colliding and moving around with each other, just like you had a distribution of velocities for these particles, right? That basically necessarily implies you have a distribution of energies also, right? And in fact, what would be your guess for what this distribution should look like? What's the name of this distribution? It's the same thing as before. It's the Maxwell-Boltzmann distribution again, right? Except instead of looking at it in terms of the particle velocities, we're going to look at it, one level up at the level of energies. Okay. So it's again a Maxwell-Boltzmann distribution. So in terms of energy, the Maxwell-Boltzmann distribution looks like this. It's 2 times the square root of E over pi. I mean, you could write this down yourselves because it's really just the same thing as what we had before. It's just factored in different ways to make it convenient for us to work with. Okay. So again. Okay, good. So now what we want from this probability distribution, though, is the fraction of these particles that are above a certain, some energy that we care about. We're going to call it EA, right? Like we did with the reaction scheme, with the reaction coordinate diagram. So what mathematically do I need to do to find how much of this probability distribution exists above some threshold energy EA? Who wants to tell me? What's the mathematical operation I need to do right now? Yeah?
You just integrate from the threshold to whatever is the end.
Yes. So if I want that fraction above EA, that's just the integral from EA out to infinity, right, of this probability distribution. And again, you can plug this in, do this integral. It's very similar to the velocity integral. It's another, you need to do one integration by parts to get the answer. I won't do it here, but it ends up with a nice, very pleasingly simple answer, which is that this fraction is just E to the minus that activation energy divided by kBt. Okay? So it's exponentially suppressed. So, and this kind of intuitively makes sense, right? Like, basically the higher that barrier gets, the harder it should be for particles to collide with enough energy to actually hop over the barrier and make the product. So now what we can do is we can combine the answer from number 1, which was here, right? So the number of times A and B collide, and the answer to 2, because that's the second half of this rate that we need here, right? And that gives us this formula for the rate in terms of these sort of really microscopic level of description. So the overall rate of the chemical reaction is going to be pi sigma AB squared, so that collision area squared times 8 kBt over pi m e to the minus EA over kBt times the concentration of A times the concentration of E. Okay. And this giant mess of stuff with all the microscopic details for the next 5 weeks, we're going to call this K. It's just a reminder. So the reason why it's important to get into this stuff is it is also a reminder of the kinds of assumptions that we're making when we do, in fact, just call, this giant mess of stuff K, right? So can you think of some limits? What are some of the hidden assumptions we made in order to actually have this be a reasonable description of the chemistry, of the physics going on?
There's no like orientation, guided reactions. It's not
so that's right. These are perfectly symmetrical balls that just hit each other with, they're just random collisions, right? Yeah. No details of the molecules. Yeah.
Like there's no attractive or repulsive forces generating along.
That's right. That's another good one. Is that necessarily true with like enzymes and proteins and stuff? Sort of. Yeah, but they have charges on them and stuff, so it's like a little dicey. But they're very, very much stuff level. What else?
I guess you're not really considering like the possibility of 2 molecules of like A and 2 molecules of B colliding.
That's also true. Yeah, and actually along those lines, what's another actually a pretty terrible assumption in this whole thing? Yeah.
But there's no reverse reaction?
Okay, that in theory we could build in. So that I think we can get away with. Yeah. Okay, so there's one which is like that at a given time step, we're only assuming that you can always have just 2 things hitting each other, right? But what happens if like this volume I drew was like 4 little balls in this giant box, right? What if you have lots and lots of them? What if they start jamming with each other, right? Is it really going to be fair to make have it just consider like pairwise collisions like that? At some point, these systems will get so this is what's called the dilute limit, right? So this kind of chemical kinetics works when systems have very few particles given the volume that they're occupying, right? So you can always break it down into these pairwise collisions. But if you have for example, the membrane of the cell, that is a terrible assumption for the membrane, right? Because they're like packed up against each other. So in cases like that, this kind of assumption can in fact break down. So keep that in mind when we are actually analyzing these systems, both in the class and in the future when we use this stuff in real life. This does come with certain assumptions that may be, in some cases, strongly violated by the actual systems you're studying. Yeah.
I don't know if this is an important assumption to think about, but is it possible that A and B could collide with too much energy?
Too much energy. Okay, so in this specific scheme, we have made it so that is not a bad thing because these are infinitely strong skiers, basically, right? But you could imagine cases where, like they hit each other so hard that they actually like fragment or turn into other things. Now, at the scales we're working at, that's in terms of energies and temperatures and stuff, that's probably not usually an issue. I think they won't actually, after all, the real molecules have like mechanical bond, they have those bonds that they have mechanical properties and vibrational modes and stuff that in theory can be broken if you hit them hard enough. But I think at the energies that biochemical reactions typically occur at, that's usually not an issue. Yeah.
So like in this model, obviously there's only 2 types of particles. So like, to what extent would it affect it if like there's something else in the mixture?
Okay, yeah, that's right. Even if you did this completely correctly, what you can in fact make that precise. The bookkeeping gets harder because now you got to keep track of like which pair, the sizes of all these different things. I did suppress one detail, which is this M. No one really asked where that M came from. I didn't say whether it's MA or MB, right? It's actually what's called the reduced mass of the system. It's the center of mass, basically. That's a little bit beyond the scope of the class. That has to do with converting this 2-body problem into a 1-body problem, which we do in classical mechanics all the time. So the reduced mass will become more complicated in a 3-body system. Yes. But you can in theory map this formally onto an n-body system.
to assume that this box is like a vacuum basically, or like would it not matter if there's like some other gas in there since it doesn't, like you can assume it doesn't interact, like
Or how about a fluid with a really high viscosity?
yeah, so doesn't matter, or
Yeah, it does, right? Because so exactly. So we assume that these are just particles in a vacuum, basically. That they just are dealing with kinetic energy. There's no friction in this system, right? There's which is. I mean, the cell has tons of gloppy stuff in it, right? You're constantly burning energy. You're dissipating energy through viscous friction, right? We are ignoring that in this description. And yes, that of course that'll absolutely matter. In fact, it turns out in recent research, these mechanical properties of things like the cytoplasm depend a lot on actually the activity of the cells even. So if you kill metabolic activity in the cell, the material properties of the cytoplasm change profoundly. They become like glasses, basically. So yeah, that stuff matters a ton. People have ignored it for like 100 years, and only now we're paying the price for it. Yeah. All right. So this is so now at least now we're gonna do for the like I said for the rest of the next couple of weeks we're just gonna call this KAV. Okay. So we'll come back to this later though. It'll be absolutely crucial for simulating these kind of systems, which we'll come to in week 6. Okay. So now that we are satisfied that there is in fact rigorous physical basis for this science of chemical kinetics, now we can sort of be users of it, right? And now we can go back to our analysis of enzyme kinetics that we sort of left off with at the end of the first lecture. Will anybody be mad if I start erasing this stuff? It's all good? Okay. Okay, so let's go back now to our McKelliff-Menton scheme. So remember what we had was that we had some enzyme plus a substrate, and now we're already going to get more complicated reaction schemes than what we actually derived all this stuff for. So we're just going to be blind to those details. It can bind, these enzyme and substrate can bind and unbind to form this bound complex, enzyme-substrate complex. And this enzyme-substrate complex at some rate will produce a product and recycle itself. So this kind of enzyme kinetics is core to a lot of the kinds of biochemical processes that occur in cells. So it's a good place to start applying the kind of kinetic theory tools that we've learned to real systems. And you'll remember last time that the goal of this exercise is to compute the rate of product formation, which we're going to call the V, or the velocity of the reaction. And chemists got jealous of physicists, and so they gave this name velocity. Okay, so let's write down the differential equations. So you remember that the way this works is we're going to take these rates, combine them with the concentrations of these different reactants as ways to describe how these quantities change with time. Okay. So dE dt, so E is created from the breakup of this complex at some rate k minus 1. So I'm going to write k minus 1 times ES. This enzyme is also produced by the productive reaction, so reactions that overcome this energy barrier. So K2 times ES. And they get taken out by the binding reaction of E with S. Okay? So that's going to be K1 E S. The SVT only has two things going on, right? So DE is the enzyme is the most complicated because it sort of occurs in every single step. The substrate and the product are both a little bit simpler. So S will disappear. Will appear with the unbinding reaction, and will disappear in the binding reaction. The enzyme substrate complex, this is the last one that we'll have to really write out fully. It does a lot like what the enzyme itself does, right? It appears in a lot of these processes. So it gets formed when enzyme binds substrate. It goes away when these two things unbind. And it goes away when the product gets formed. Okay, so these are the three governing reactions in the system, right? And this, we don't need to write down a differential equation for the product formation because that's actually what we're trying to compute. We're trying to compute what this EBDT really is. Okay, everyone with me? All right. So one thing that we've said before is that enzymes, right? The key property of an enzyme, the two key properties of an enzyme, one is it reduces this EA, right? It reduces the activation area. We're not going to get into that. So. The other key property of an enzyme is it's not consumed in the overall chemical process, right? You regenerate the enzyme at the end of the day, right? So that implies that there's a conservation law. In this system, right? And that's that if you add up the concentrations of the enzyme substrate complex and all the free enzyme, that should be some fixed number that we're going to call E sub T, E total, right? Everyone agree with me on that? This mathematically enforces that condition that enzymes are neither created nor destroyed in the overall chemical process. Okay, why is that useful? Why is that useful is that allows us, because we know that ES and E are subject to this constraint, that means that we can actually substitute in one of these variables for the other, right? And reduce this set of equations by 1. Right, because of this conserved quantity. It's not an open system. So what we can do, for example, is we can take this, let's look at ds dt first. So ds dt, remember, has this enzyme substrate complex concentration built into it for this one way to regenerate it. Right? So what we can do is well, also it has this guy in it, right? It has the free enzyme in it also. So we can now which one we pick to get rid of is up to us, and you can do it either way. It doesn't matter mathematically. But let's choose to get rid of this guy. Okay, so we're gonna take this E and use our conservation law to get rid of it. So now we're gonna have E equals ET minus this bound state. Just skipping ahead a little bit, why do you suppose I picked that one instead of the other one? There is a little trick to this. It makes our lives a little easier. It's mostly because this product formation rate is only going to depend on this concentration, right? So we want to keep this one around. This one is actually kind of useful. Okay. So if you do that, substitute that out, you get the same. So and you do a little bit of rearranging. You can rewrite all these in terms of these. So you can substitute this into this right here, and then just distribute terms. And you can do the same thing with another reaction with the enzyme substrate dynamical equation. And you get K1, ET, S. Okay? So we've turned that 3 equation system into 2 by substituting the free enzyme for the total minus the bound complex. Okay. Now we're still stuck with 2 of these guys, and we still, remember the goal eventually is still to compute this guy. And let's just start writing out what it actually means. Okay. So we're close now, right? So what we still need to know, at a given moment in time, for example, what this enzyme substrate complex concentration is in order to actually compute the velocity with which the product is made. Okay. So at this point, enzymologists sort of threw up their hands, like, okay, I don't know what to do. And then in sometime around 1910 or 15 or so, this biochemist named Haldane, so J.B.S. Haldane, they were working on trying to analyze these kind of systems theoretically. He had this really great idea, which is, what if we assume that at any given moment in time, these processes happen really fast. Okay. The product formation, the substrate consumption, and the enzyme substrate rate. If those things happen really fast compared to this bottleneck reaction at the end, so we'll assume that the product formation is really slow, then at any given moment in time, these dynamics can be completely ignored. Okay. Right? So the time derivatives of these 2 quantities can be set to 0. Okay. And once you set this one to 0 and then solve for all these variables algebraically, you can get a formula for this product formation rate, right? And we assume that one is the slow thing that we're trying to actually compute. So you use this Haldane steady state assumption to say that this steady state is 0, is in steady state. Okay. So what that does is it gets rid of another reaction, right? So now this is set to 0. So now what you can do is if you set this derivative to 0, this becomes an algebra equation, right? So you can solve for that, right? So if you solve for that, what you get is that the steady state enzyme substrate bound state is just K1 times S over K1 S plus K minus 1 plus K2. Okay? And you can rearrange, okay, so that's great, right? Because now what we can do is we can plug this into this equation, into the product formation equation. And if you do that, you have an equation for product formation. So it's just K2 times this mess, right? K2 times S, K1S plus K1, K2. Okay. So now we have an explicit equation for how fast this enzyme is able to turn this substrate into product. Yeah.
Sorry, I had a question about that step, the second line that you did there.
Yes.
Where we make the assumption that the rate of ES is 0. So for that, on the second board, do we just set like that DE over D, ES over DT equal to 0?
Yes.
And then, so why do we lose ET on the right side? So the numerator is K1S, but there's no ET. I was wondering if we made this assumption.
Oh, sorry, yeah. My mistake. This is all multiplied by ET. I just forgot to write it down. Yeah, so this is like a fraction, right? It's a fraction of the enzyme that's bound in this complex. So yes, good observation, yes. So what you can do with this equation is actually you can rewrite these terms. You can relump them in different ways. So you can divide this out by K1, right? What's that?
There should be a K1 in the numerator.
The K1 in the numerator? Yes. So you can divide out by K1, that cancels this guy, and brings the K1 to this lump thing here. And then you can say that these two things go together, K2 times ET. Okay? So this thing we're going to call Vmax. That's basically the maximum rate at which this enzyme works. And this thing we're going to call Km, which is kind of the concentration. This, if you look at the units of this carefully, you'll see it's units of concentration. This is the concentration at which the enzyme starts to saturate. And so you end up with this equation that's Vmax times S over Km plus S. All right. So this gives you a an equation for the product formation rate as a function of substrate, and this is the heart of like basically what we'll use as models for more complicated systems that we'll get into starting next time. All right.